Let's look at an example of an experiment that involves choosing two people to see if they're in favor of genetic engineering. The first thing we're going to do is to draw a tree diagram of our experiment. So I'm going to ask one person what they think about genetic engineering. They might say, yes, I am in favor of genetic engineering, but they could also say, no, I'm not in favor. Now, what if they said yes? Then what? Then let's ask the second person what they think. They might say yes, they might say no. However, what if this first person said no to start with? Then what? Then the second person might say yes, or the second person might say no. So I have the outcomes over here. If I follow these tree branches, I get yes, yes. If I follow these tree branches, I get yes, no, meaning that the first person said yes, they're in favor, and the second person said no. This set of tree branches means the first person said no, but the second person said yes. And this set of tree branches means that the first person said no and the second person said no. So our sample space would look like this: yes, 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 no, no, yes, and no, no. If we go over here and look at our questions then, what's the probability, here's question A written in probability terms, that both are in favor? That is, the first person said yes and the second person said yes. Well, since these are all equally likely outcomes, we don't have any information suggesting that more people feel one way or the other. One of these outcomes of the four fits this description, both are in favor, so our probability is 1 out of 4. What's the probability that at most one? Well, at most means you can't have more than one, but you could have less than one. So at most one is against means I can't have more than one no. So this outcome doesn't match the description of at most one, but these other three do. Because I could have 0 against, I could have 1 against, but not 2. So 3 of these outcomes fit our description here. Now that's different than exactly 1 being in favor. At most 1 is not the same as exactly 1. How many of these outcomes have exactly 1 yes in them? Well, that's these two. So there's 2 of our 4, which of course reduces to 1/2, that are in favor of genetic engineering. So that's how you can use a tree diagram and a sample space for that matter to come up with some probabilities. So what's probability? It's just a numerical measurement. It tries to come up with a way to tell us how likely some event will occur. Now there's 2 rules to that. One of the rules is this: the probability of one thing happening always has to be in between 0 and 1. It can't be less than 0 or greater than 1. And the sum of all the probabilities of all the outcomes. So if I look at all of these probabilities that go with each one of the outcomes, the probability of yes, yes, plus the probability of yes, no, plus the probability of no, yes, plus the probability of no, no, has to add up to 1. That's what this last bullet point here is talking about, sort of like our relative frequencies. Now, classical probability, don't worry about the terminology. That just means this is how we typically calculate probability. Just like I went through, there were 3 ways that we could get at most 1 being against. So that's the number of outcomes in my specific event, 3, divided by the total number of outcomes in a sample space. So you guys are really familiar with that type of probability. If I roll a die, what's the probability that I would roll a 5? Well, since there's only one way I can roll a die and get a 5, it's 1 out of 6.